So this kind of wave dynamics actually we can see in the real-time observations. So you can see here, this is the Topex Poseidon sea surface height deviations for the 1997 El Nino event. You can see that these are the Rossby wave, upwelling Rossby wave because of the reverse in the wind. We already have the El Nino, and they are now going to the coast and then reflected back near the equator as upwelling Kelvin wave. And eventually you can see in 1998 February, these Kelvin waves are now propagating eastward to the eastern Pacific, and eventually they reach the coast, and you can see by May we already have cold anomalies in the eastern side. And the opposite thing happens during El Nino, before the El Ninos. So instead of cold anomalies, we have warm anomalies. They propagate to the Indonesian coast, Philippine coast. Then they reflect to the equator and return back as warm Kelvin waves, bringing warm waters to the eastern side. And that's why El Nino sets in. Similar thing happens in the Indian Ocean. I will go to that later. So this is how it happens. Different phase of El Nino, La Nina, La Nina, El Nino, and La Nina cycle for the 1997 El Nino event. 1996 August, you can see that warm water, off equatorial warm water propagating as Rossby waves. So these are warm water being brought to the coast, to the Philippine coast and the Indonesian coast, then reflect as Kelvin waves. So now we have warm Kelvin wave. You can see March 1997, the warm Kelvin waves are propagating from the western side of the Pacific to the eastern side of the Pacific. And then by December, it's fully established. So eastern side is very warm because of the Kelvin water bringing all the warm water here. And then the winds are now reversed. So they are upwelling favorable. So we have upwelling in the off equatorial regions. And these upwelling Rossby waves propagate to the coast and then reflect as Kelvin waves. And you can see by August 1998, these equatorial upwelling Kelvin waves bring cold water to the east. So eastern side gets cooler, and toward the end of 1998, we see a La Nina state. So that takes about 2 years, from August 96 to August 1998, and the Kelvin and Rossby wave can explain that. If you compare that with the theoretical model presented by McCrary in my previous slide, it takes 1 year. In reality, it is more than 1 year, like it takes 2 years here, as you can see. That is because a lot of other variability influence these ocean dynamics. So that's why they slow down the Earth's interactions and other noises. They slow down these wave dynamics, and that's why it doesn't happen in 1 year. It happens in 2 years, and sometime in 6 or 7 years, because of there are many other factors influencing the simple ocean dynamics. And there are also other theory. This is a quick animation of what was happening in 97, 98. So this is the La Nina happening now, and the El Nino stars. There are other hypotheses that also try to explain the El Nino and La Nina state. One of them is delayed oscillator. So delayed oscillator is basically similar to the dynamics we saw in previous slides, but there are other factors, the Earth's interactions and other noises included in that to make the wave dynamics slower, and that's how that theory can explain the periodicity in the ENSO phenomena, why it happens sometime in 2 years, sometime in 5, 6 years. The other hypothesis is recharge-discharge mechanism. It is basically similar to the Urki mechanism I showed you before. The warm water volume build up and then discharge, and then La Nina happens, and then gradually the warm water volume builds up, then next El Nino happens. So El Nino discharges the heat, and then once it is discharged, La Nina sets in, and then slowly warm water gets built up in the Western Pacific. And then when it reaches a critical value, it goes into discharge, and then the El Nino happens. So that's the kind of warm water volume recharge discharge mechanism. But on top of that, the hypothesis adds the Earth's interactions that can delay the process sometime, or maybe make it quicker sometimes. So that's how it can explain the periodicity in the ENSO evolutions. There are several kind of advantage and disadvantage to each of those theories. Like for example, discharge mechanism is closer to Urquist's build-up mechanism. It has memory. It has also Earth's interactions that can delay the process. To some extent, it is better than the wave dynamics we saw before. Also, the other hypotheses we saw before they also have their own advantage and disadvantage. Okay, so once El Nino happens, it has large-scale global teleconnections. So immediately, because of the warm water, we get very wet conditions in the Eastern Pacific, and because the moisture is taken away from the ocean side of the Pacific, so the maritime continent is dry and cool. The temperature is cool because the warm water is taken away to the eastern side. So cool and dry on the western side, leading to drought, sometimes forest fire, etc. And the eastern side is flooded and warm and wet. Similarly, India is dry and wet. Several parts of Africa is kind of wet and wet and also dry. Also, there are large-scale teleconnections which can bring the information from the tropical Pacific to the high latitude in the northern hemisphere and also in the southern hemisphere. So you can see cool temperature when El Nino happens. The western side of America, United States of America, is wet and warm, but the eastern side, including Canada, is cool. And this is the teleconnection that is happening because once we disturb the atmosphere there, that creates kind of high pressure in the mid latitude, then low pressure in the higher latitude, leading to high. And this high low high is called Pacific North American teleconnection. Similarly, we have Pacific South American teleconnections, and that's how the information is taken to large part of the Earth. Now, once we know that these are the climate phenomena that has some dynamics, and because of the dynamics, ocean dynamics, it has predictability, and that's why initially people try to use simple models to predict El Nino, La Nina, but then the global models came in with the global atmosphere, the global ocean, and then coupling them, we can produce global scale coupled models that can simulate not only El Nino or La Nina, but other climate phenomena and their teleconnections. And the model we are using at JAMSTEC is called SINTEX Frontier Model. SINTEX stands for Scale Interaction Experiment. Frontier was the original name of my institute in JAMSTEC, and this model is developed in collaboration with several European centers. The atmosphere model ECAM is coming from the Max Planck Institute. The ocean model OPA, now NEMO, is coming from Lausanne in France, and the coupler also, Oasis coupler also is coming from France. And we have this coupled model developed by the CMCC in Italy, and we brought it to the Earth simulator, did the bug fixing and several kind of parameterization, and now we have the model which we call the SINTEX F1 and F2, and we have now F3. These are the models. They are one of the best model. This is one of the best model in the world to predict the El Nino and the Indian Ocean dipole. I'll come to the Indian Ocean dipole later. You can see that for the El Nino, these are the lead months of the forecast. For example, if you start this month, this and this forecast will tell you, and this month is January now, so this will tell you up to July what will be the El Nino condition. And El Nino condition here we are represented by one index. This is the Nino 3.4 index, which is the average temperature in the Eastern Pacific. So if it is higher than normal, like 1 degree centigrade above the zero line, then that is a strong El Nino. And if it is below -1 degree centigrade, then it is a La Nina condition. So we have observations of El Nino, La Ninas for a long time period, and then we do the model simulations for, like in this case the model was simulated from 1982 to 2001. Now the present version of the model is simulating until 2026. So we have all the predictions from 1982 to present time. What we do, we correlate this model predicted Nino 3 index with the observed Nino 3.4 index, and Nino 3.4 index from model, Nino 3.4 index from the observation, and that correlation is given on the y-axis here. So you can see that the correlation at 1 month lead time. So we are predicting this month for the next month. So this is the February correlation between the observation and the model prediction. So you can see it is close to 1. And as you go to 6 months, the correlation drops down, but it's still above 0.85, which is considered as very high skill. Anything above 0.6 is reliable. We consider it is reliable if it is if the correlation is above 0.6. In this case, at 6 months lead time, you can see the correlation is close to 0.9. So that's why it is very reliable. The model, and there are the other models. These are the other models. You can see the red line is Syntex F model. You can see it has the best skill for this kind of setup at that time compared to any other models. The black line here is the persistence. So if you don't have any model and you just consider today's Nino 3 index is same as next month, next to next month, and 6 months ahead, then you will be probably right for first 1 or 2 months, but then the skill drops down. So anyone cannot guess what is going to happen for the Nino 3 index, but the models are able to predict them. And Syntex F is the best model in the world that predicts the Nino 3 index. This is how the Syntex and any coupled global models are configured. So you have the grid points. The atmosphere is divided into many grids covering the whole globe, and similarly oceans are also gridded. We have some problem for the North Pole and South Pole. So usually in the ocean world, in the computers, the pole is over the land to avoid some kind of singularity at the North Pole and South Pole. But that doesn't affect the temperature, the currents, the salinity simulated by these models. And then they are coupled through several ARC fluxes, the latent heat flux, the sensible heat flux, the radiation coming from the sun, the long wave radiation going out of the land and oceans. And all those interactions are included as fluxes in the model, and they're actually the atmosphere model, grid point model, and the ocean grid point model. They are kind of interacting. There are several ways of solving these equations. People use different techniques: spectral technique, numerical technique, finite difference, finite element, and different kind of techniques. And each of those models have advantage and disadvantage, and also the grid systems are different from model to model. They have also advantage and disadvantage. The model we are using is the spectral model for the atmosphere, and the grid point model, finite difference model for the ocean, which was OPA, now is NEMO.